Right. How will you know? Can you hear? Is it on? Is that better? Do you think that's all right?
You will have to project your sound.
Right. Okay. Right, so hopefully engineering department is there as well. Okay. Hi guys. Did you all pick up handouts? Great. So we've printed many, many more than there are of you. That's quite a lot more. So what you've got, it turns out, is the handout from last year, which is fine because the text is all the same, apart from the little spiel at the beginning, which talks about probably exams. It's like the administrative bit for 2017. So if you want to refer to the website just for that first 3 pages. But otherwise, the text is all the same. So you know how this is going to work this year, right? You haven't got exams. You've got to do this practical instead. That's true whether you're MPhil or Part 2. So what I thought I'd do is just deliver the material that we're supposed to deliver, but also just add some interesting bits in here and there that I hope might be interesting to you and that might lead you to some thoughts for when you're doing your practical. So, okay, today we're doing morphology. We're going to just talk a little bit about what it is, why we use it in NLP, and the methods by which we've more or less solved this problem for English anyway. And then we might think a little bit about why the problem isn't necessarily as easy in other languages as we go. Right, so last year when you did formal models, we did the formal stuff, but we didn't talk so much in detail about what goes on in different languages, right? So we're going to concentrate a little bit more on actual natural languages this time. And so I'm going to, as we go along, I'm going to assume that you know the stuff from the formal models lectures, which means if you're an MPhil or in the engineering department and you don't know what I'm talking about at some point, you need to go and look at the 1B slides for computer science formal models of language. Okay, right, so what is morphology? Morphology is the study of the structure of words. And in order to talk about the structure of words, we're going to use some terminology. So what words have we got? We've got a morpheme, which is all of the minimal information carrying units of the word. So we're going to break words down into pieces, and the way we're allowed to break it down is if a unit carries some specific information. We're going to have affixes. Affixes are things which can't occur on their own. Another word for bound morphemes. So these are morphemes which have to occur in the presence of some other morphemes. And in particular, there has to be a stem. So usually we have a stem and an affix, or many affixes. And so stems we can call, they're usually free morphemes, certainly in English. That means they can exist on their own. And compounds are words which have more than one stem, so more than one meaning unit in them, which could possibly exist on its own, and contributes to the main meaning of the word. So notice things like this. We can't just divide the words up any old how that we like. So even though we've got things like slither, slide, and slip, which clearly have something in common, we can't take the SL and just say it means something slippy or slidey, because all of these other pieces aren't meaning units on their own. So IDE and IP and ITHER, they don't mean anything. Okay, so breaking off the SL here would not give us some morphemes. They have to actually leave us with pieces that always are meaningful units. Okay, so affixes come in various forms, and I've got our examples here from English. So we use a lot of suffixes. That's just adding stuff on the end. We use prefixes, particularly in derivational morphology. I'll explain what that is in a second. In English, we don't really have infixes, but you can do things like this, which tells us something interesting about how words are composed inside our head, maybe. And we don't have this idea of a circumfix. That's an affix which goes around the word. We don't have that in English at all, but languages like German very commonly have this. So this affix here, GE with a T, that puts things in the past tense, and you just insert the stem inside. Now, just as a point of interest, the way that they are ordered on the slide here actually turns out to be the frequency with which they're used in different languages across the world. So circumfix is actually quite rare. Right. So we've got different types of morphology. The first one we're going to talk about is inflectional morphology. Now, inflectional morphology is when we have morphemes which add something to tell us about something linguistic. They tell us about tense, aspect, number, person, gender, or case. So this is when we take a stem, we put an affix on the end, and it tells us something like, this is now a plural, or this is the first person, so this is me that's doing it. So the inflectional morphology is when we add morphemes that tell us something, that change the linguistic nature of a word, but it doesn't change the meaning of the word, it just tells you more about how it's happening or who was doing it, okay? So examples in English, if we add an S on the end, we get either the third person or we get plural for a noun. If we had a verb, I play, but he plays, so the plus S suffix tells us that it was he or she that was doing the play. And the ED affix tells us that something happened in the past. So these are inflectional morphemes. The inflections can sometimes be referred to as a paradigm. So that's when we take the stem and we list all the possible ways we can grammatically alter it using our inflectional morphemes. We call that the paradigm. In English, they're very simple because there's very little inflectional morphology, but this doesn't work. For example, here is the word the in German. So where we have the word the, they have all these different variations of the word the, depending on the linguistic context in which it's used. So it depends on whether the noun is masculine, feminine, or neuter. So this is we don't have this in English either, but they have different classes of nouns, and also how the word is being used, whether it's the person in the subject or whether it's something that's happening to somebody else. So this changes how the word the is used. And this is the inflectional paradigm for that word. Okay, so that's inflectional morphology, does something linguistic to the word, tells us more about how or when or who. Derivational morphology, on the other hand, is morphology where we add morphemes that can change the meaning of the word. So, for example, if we have un, that obviously usually changes it to some sort of opposite. And it can be quite extreme the way that the nature of the word is changed. So it can actually often change part of speech. So we get adjectives going to verbs, going to nouns, or we get verbs going to nouns, or nouns going to verbs. So this is an example here. So if we have the verb help, if we add the suffix er, it changes it from a verb into a person, a noun. So we've got actually changing the part of speech by using this thing. We can keep adding the derivational morphemes as often as we like. We could make the words as big as possible. So what have we got here? Anti-disestablishmentarianism. I guess you could have anti-disestablishmentarians. You could go on forever. So derivational morphology, you can theoretically add as many as you like. It changes the meaning of the word entirely. And it's as different to inflectional morphology, you can have a large stream of them, where it's inflectional morphology, you sort of fill up the gap. You know, you can put past tense on or not, but you can't put past tense on many times to say it happened in the past, you know. So different sorts of, different sorts of morphology. So how does this work in the world? I've just shown you examples from English just now. But what kind of things do languages do? Well, there's actually all kinds of different ways they can carry their morphology. So at the most extreme, we've got something called isolating languages. Isolating languages have a very, very low number of morphemes per word. An example is this language Yoruba. Chinese is often thought of as being a kind of isolating word. So the idea there is each unit carries some meaning, but you have to get across the other meanings, like things about when it happened or where it happened, by some other means. And that can happen by maybe fixing the order. So you say that the person who does an action is always at the front of the sentence or something like that, but they have to get across the same information by using a different mechanism. So fixing the word order or using extra words to indicate that something, how something happened or when it happened. So isolating languages is the most extreme with the lowest number of morphemes. Synthetic languages is the name given to all languages that have a higher number of morphemes per word. But they can be subdivided into different categories. Agglutinative languages are ones where you've got, for the inflectional morphology, in particular, you've got each kind of thing, like tense or aspect or person, having its own little affix, and you just keep adding them on. So if you've got something happening and it's happening in the first person and in the past and et cetera, et cetera, et cetera, all the little bits of information you can have, you keep adding more and more inflectional morphemes to show all that information. Inflected languages carry that information in a single unit. So for example, if you think back to your study of French or Spanish or whatever you did at school, if you think of the ending, say, for plural you on a verb as opposed to singular, then you've just got one ending. And the fact that it's plural and second person is embedded in just that one ending, as opposed to the singular singular second person. So if you see what I mean, you've got more than one piece of linguistic information embedded into one particular morpheme for the inflected languages, but for the agglutinated languages, we don't combine them. We just keep adding separate ones that always keep their meaning. So an example of an agglutinative language is Turkish, and then the Romance languages tend to be inflected, so they carry more than one piece of information, the inflecting morphemes. So what is English? English is considered to be an analytic language. What does this mean? It's almost isolating. It's got very, very little inflectional morphology. I mean, the two things I put up, the S and the ED, what else have we got? ING, very little else. We have very, very little inflectional morphology at all. And we use helper words and word order in order to tell us the stuff that in other languages is explicit in the word because of the morphemes. Now, we're not actually an isolating language because we use loads of derivational morphology. So morphemes do exist, and we have not a very, very low inflectional morpheme ratio per word. We actually do have a reasonable ratio per word, and that's because we use a lot of derivational morphology. So we are an analytic language. Is anybody interested in why this is the case? There's kind of all kinds of theories. I'm going to take a second just to explain one of them. So yeah, the idea of why we've ended up this way is actually because of all of the different language influence we've had over time. So there's this idea that if you have very many second language learners in a language, the inflectional morphology is actually quite difficult for people to pick up. So doing things like fixing the word order and having the person doing something is always at the front and the person who is acted upon is always at the end, that is a more salient way of communicating if you've got people who don't quite all speak the same language. And we've had quite a lot of movement of different peoples in the country, which has ended up to, over thousands of years, us being an analytic language. That's one of the theories why, which I think is quite interesting. Right, so let's have a look at this a little bit more. So we have a mix of all of these different types of morphological features from the different possible ways of building up a language. We do have suffixes for inflection, but we don't have very many. We also have this kind of inflection through sound change. And this is, again, a historic remnant. So this is one of the earlier languages. And these have kept on in English because they are sort of high-frequency words. So we have things like sing, sang, and sung. So this is actually called ablaut morphology, where the sound changes to indicate something inflectional about the word. But this is no longer productive in English because you can't have something like, if you were going to ping someone on a computer, you can't pinged. It's pinged, pinged, and pinged, not ping, pang, and pung, right? We don't pung people. So this kind of pattern here is a remnant and is no longer productive in the language, whereas our other affixes are. If we coined a new word and we wanted to put it in the past tense, we would probably add the ed on the end, for example. So we've got some of these remnants, which means we aren't completely regular. We've also got weird stuff like this. So go, went, and gone. Where does this come from? And good, better, and best. Right, so these are also remnants from earlier English. So go and gone, clearly quite similar, right? So go in the past tense, something has gone. They come from the same word, so this is an inflection of go. Where does went come from, right? Go, I went. That's like not even remotely the same. So what has actually happened here is this is two different words that have ended up, which both would have had their own inflections at the time, and we've amalgamated them, and it just so happens that the went, which comes from the word wend, has stuck as our past tense preference for go. So that's why we've got, this is basically the inflections from two different words which have ended up with one meaning and sort of more together. And we've got the same thing with good, better, and best. So good comes from something like the Old English to like stuff to hold on to. And this better and best comes from a word which is more like a solution, right? So yeah, what's happened here is, again, you've got two different words which would have had their own inflections, which have come together to make, give us our superlatives, but not in a way that makes them look regular. So we've got all these historical remnants from the fact that we've got all these different words coming in. Okay, so for inflectional morphology, we've got some regular stuff, majority regular stuff, and then we've got these historical irregular things, which tend to be high-frequency words. That's why they've stuck around. But for derivational morphology, we use both prefixes and suffixes in our language, and we also have this case, especially with modern words, of zero derivations. So I can change tango or waltz into a noun or a verb by doing nothing. The dance tango is a tango, but I would also tango if I was dancing, right? So we have instances of zero derivational morphology here as well. So we've got all kinds of stuff going on in English.
Sorry, just quickly. Can you explain that changing between a noun and a verb, isn't that presenting the information elsewhere in like an isolating language where you present it elsewhere in the sentence or the structure of the sentence?
For what? For the zero derivational ones, you mean?
So for I tango versus tango as a dance, it's presenting the information as to whether it's a noun or a verb elsewhere in the sentence. Isn't that a bit like isolating languages, or is it somehow different? Yeah, no, that is rather like isolating languages. So isolating languages and analytical languages are quite close, and the only difference being that we have much more derivational morphology, whereas they wouldn't. Yeah? Yeah.
The past tense of the verb.
Yeah, that's right. So they have like an indicator in Chinese, where you would basically say, you put this indicator function, and then you know that all of the things you're talking about happened in the past. They also have sort of slot order as well, like I think it's 8 types of place where you would, the order in which you would present the information is fixed.
Context-based in this case. This is more context-based, whereas that's more structure.
Yeah, well, we use structure as well because we always, well, most often do subject, verb, object. Okay. Yeah, well, we won't go more into it now, but if anybody wants to speak to me about the etymology of words, actually come and speak to me afterwards. Love it. So it's, yeah, just come and talk to me. Right, so we've thought about a bit how morphological structure can go on across languages and what goes on in English. Now, unfortunately, like everything in natural language, there is a lot of ambiguity in the way we can break the words up. So there's some structural ambiguity with the stems and affixes. So for example, if we have paint plus S, then paint could be a noun and a verb, and it doesn't help us to know there's a plus S affix, because if I have paint, I could have paints, and if I'm painting, I paint, but if he is painting, he paints. There's no way to tell through the splitting up the stem and the affix whether we're talking about nouns or verbs. Okay, so there's some ambiguity there. Then there's the question of where we even split things up. So the example we've got here is shorts and shorts with the S. So short, if I'm wearing shorts, I would never take the S off. That is, in fact, the entire stem of the word. But if I was drinking a short or shorts, I would want to take the end off the word, right? So it's not clear just by looking at the fact that there's an S here that we would always want to remove it. Then we've got ambiguity even in things like compounds. So here we've got blackberry, blueberry, strawberry, cranberry. So a blackberry is actually a blackish berry. Blueberries are bluish berries. So you can imagine that actually you've got two sort of stem words going together, giving you description of the whole thing. But by the time we get to strawberry, they're not made of straw or anything. They're actually grown in straw, or used to be, which is, I think, where that might come from. Cranberry isn't a thing, right? A cran? No. So even though we've got the same type of word going on here, we can't even just chop berry off the end and get meaningful units every single time. Okay. Then we've got things like this word here. And it could be split up into either unionized or, if you were doing chemistry, unionized. So it completely depends on the context how you might split that up. And you then need to think about how the bracketing would work. So an union on its own is not a possible thing. So we actually want to arrange the bracketing so that we've got ionized in the middle and ionized all together and un right at the front, because actually un has got two meanings as well. So with a verb, un means to do the reverse. So if we tie, we can untie. But with adjectives, we've got, it means that it's not. So unwise and unsurprised. So here, because we've got a verb, we need to have the un put in front of the whole thing. So we've actually got a bracketed, nested structure for this particular derivation or morphology. Now, for those of you who can stretch your minds back to the formal models, the fact that we've got brackets in here is going to tell us something about the way we might want to model these things, right? So if you remember, when we looked at regular languages and finite state machines, we always ended up with a structure which only gave us a left branching or right branching tree. Now, it doesn't give us this kind of structure here, which would be a sort of more bushy tree if we drew it out with the bracketing. So we would have to decide how much we cared about this when we were thinking about how to model our morphology. It's like, do we care to keep the the structure of the word inside, or are we just trying to recognize the word? And how often does this kind of thing happen? Those are the things we'd want to trade off when thinking about how to model it. Right, so what do we even do with morphology in NLP? Right, so we can first think about whether it's possible to build a full-form lexicon. And for English, actually, that's not too bad, because we have so little derivation of morphology. So imagine you're building a dictionary, right, and you want to be able to look up a word that you've seen. So for English, actually, that's not too bad. We could have paint, we could have paints, we could have painting, we could have painted, right? And we're almost done with all of the possible versions. Now, if I was speaking another language that had many, many inflections, and I tried to list them out in a dictionary for every single one of those, I would end up with masses and masses and masses of entries in my dictionary. English is not too bad. But it does mean there's some redundancy if we start doing that, right? So we've got quite regular inflectional morphology. Is it really necessary to store all of the variants for all of the regular verbs and all of the regular nouns? Wouldn't it be just useful enough to know, actually, for any regular verb, these are the possible things we can shove on the end. And for a regular noun, these are the possible things we can shove on the end. And that would be just a much more efficient way of storing that. It also means that if a new word comes into the language, we don't have to edit the lexicon. We can just add the stem into it because we know how to handle it. Right. So ideally, the most useful thing that anybody could have is a full-form lexicon for every language. We could just do the lookup. But there are these constraints which just mean, right, it's not really practical because we've got dynamic languages, words come into it, and also for most languages there's so much inflection, this just explodes it and puts lots of redundancy in it. Stemming. So stemming we're mentioning here because it's similar to doing some sort of morphological analysis, but it's not exactly the same. So stemming is what is used in information retrieval. And what goes on there is, say you're looking up something on the web and you're really into cats, right? So you want to be able to find pictures of cats, whether you typed cats or cat, okay? So for IR, what happens is the variants of a word are all trimmed back to some canonical form. That canonical form doesn't necessarily have to have anything to do with the word. It could be a number, right? So I could represent all cats, everything that has something to do with cats as a number 53. That would be the canonical form for cat. So anything, when I see the word cat, I map it to that, and in my index, I've called it that. Now, as it happens, the stem does tend to be lexical in some way. It tends to be the first few letters of the word, but it doesn't have to be, and can often not be, an actual linguistic stem. But you can see how it would be related to the morphology. So lemmatization is this process of taking the word and trying to break it down into its affixes and its stems. And the reason we would want to do this is because it actually helps us with things that we do further along the pipeline in NLP. If I've figured out whether a word I've got is a noun in the past tense, that might tell me some things about how my syntax tree is going to look, because it can place some constraints on the way in which the syntax of the language works. There are definite interactions between the nature of the word is being used in and the syntax tree I can draw over the top. Now, again, if you remember back to the formal languages course last year, we talked about how many, very quickly you get very, very, very many derivation trees. If you've got some way of reducing the number, and that could be by understanding the morphology before you start, that would be really, really helpful. So you just reduce the number of things that you're looking at. And with this, we can often think about it as a two-way process. We might want to go from the word party, say, and say, right, we want to make this plural, so I want to get parties. Or we might take the word parties and we want to break it down and say, actually, well, that's just party in its plural form. So it's something we might want to do in two directions. Okay. Now, okay, so English actually has a slight complication, but luckily it's a fairly regular one and applies uniformly. And that's that we don't just add our affixes, we then have some phonological things, which means that the spelling changes according to the sounds that we have. But luckily, this is all quite regular. So if you think, what we have here, say I'm trying to change, I'm trying to add S's onto a load of nouns, right? Now, if I do that, I would go look at my noun. I could look up, how do I change a noun into a plural? Oh, I add an S, right? So I've got my noun. I know that I want to have a plus S affix, but now I want to know how to spell it. And in English, that isn't just the stem plus the S, mostly is, but sometimes it isn't. And the places where it isn't are luckily very regular. So we know what they are. It's whenever the word ends with an X or a S or a Z, then we add this little E sort of sound in there, which so fox, foxes, as opposed to cat, cats. So it's a different sort of S. And it comes out in the spelling as this, adding this E. And for English, this type of spelling change is completely independent of whether we're doing things to nouns or verbs. So if I am, fox is a good example, because you can fox someone as to like bamboozle them. So if I change, if he foxes somebody, then that use of foxes is exactly the same as if I've got many foxes. If somebody's not from around here, a fox is like a little dog thing, a wild dog. Anyway, okay. Here is a spelling rule. Let's break this down a bit, see what it's got. So this is saying, okay, so I've got here my box, and I'm going to add an S onto it. So we use this little hat to be an affix boundary, and we want to be able to convert it into boxes. So what we've got here on the left-hand side of this slash is what you'll remember as being something like a production rule. So we're going to map empty string, in this case, to E. And this is telling us, the stuff on the right-hand side of the rule is telling us the context in which that happens. So this is saying, whenever there's an X, S, or Z in front of the affix boundary, and there's an S after, and we're adding an S, then this little line here tells you where the position of the left-hand side rule is going to go. So we add it in here. So yeah, we've got the context in which it happens on the right-hand side. Okay. Now, as I said, this is the same for plurals and verbs, but this is an interesting thing. We can implement this as a finite state transducer. Now, anybody who did last year's course will remember that when we had a production rule altering in the context of some information, that was actually a context-sensitive grammar, right? And they were really, really expensive. And we didn't like to deal with them. But in this case, actually, what you've got here is just some terminals that the context is. And that actually means it's just telling you something about how the finite state machine is built. It's telling you about the transitions on either side, if you like. So it's not giving us the same as if this was, if these were non-terminal symbols on the left and right here, then we would be talking about a whole different ballgame of complexity. So actually what we've got here is something that we can derive with a finite state transducer. Now, we didn't talk about finite state transducers last year. Finite state machine, I think you remember, had 5 parts, which we defined it by. So you needed a start state, all of your states, a set of end states, a vocabulary, and the transitions. We'll look at one in a minute to remind you. A finite state transducer has 2 more pieces of information. Every time I transfer from one state to another on an arm, I'm going to now map a symbol from one thing to another thing. Okay? That's going to allow me to do things like change from empty string to E. So there we go, empty string to E. And so I'm going to need two more pieces of information. I'm going to need an extra vocabulary. I'm going to need a vocabulary of things I'm allowed to change into. I'm going to need the rules, another set of transition rules, which are going to say something like, if I am in state A and I see symbol B, then output symbol C. And you'll see this in a second. So it's like a finite state machine, but with a couple of extra pieces of information. Right, so what exactly is it that we need to do our morphological processing? We're going to need to have around things like affixes and their meaning. So if I want to change something into a past tense verb, I'm going to have to look up, how do I change, what's the inflectional morpheme for past tense verbs? I look it up and find it's an ED. I'm also going to have to list all of the regular forms. I'm going to need all the stems with their syntactic categories. But sometimes actually this isn't enough. If you have something like the word hang, if I'm talking about washing, I hung it up, hung. But if I was hanging someone till they were dead, then it's hanged. He was hanged, right? He wasn't hung. So you actually need a little bit more information than that as well sometimes. Okay, so this is a bit of a reminder about what a finite state machine is. There are, I think, two things wrong with this diagram. Anybody want to say what that are? Yeah? There is no starting state. So this should be an arrow pointing into here. And anything else? The one's a little bit more pedantic. There will be, because this is a non-deterministic one, but that's not a problem. That just means it's a non-deterministic finite state automata. The other problem, I think, is that we don't know what the alphabet is just from this picture, but we are assuming it's from the alphabets from 0 to 9. So if this was an exam, which I know you're not taking exams on this year, but I would not give you full marks because you were missing two of the 5 pieces which define your finite state machine, one being the start state and the other being what the vocabulary is, right? Okay, so we'll assume that vocabulary is 0 to 9 and that digit is a word which is representing the whole vocabulary, 0 to 9. So what does this thing do? It accepts things like, what have we got? 1, 1, 3. Oh, yeah. Okay, I see that. 1 digit. Yep. Okay, so if we go from state 1 to 2, 2 to 3, 3 to 4, and then 4 to 6, we can get 11, 11/3, for example. This thing also overgenerates things. So it's supposed to be generating dates. Yeah, so it's supposed to be generating English-style dates. If any of you are American, you do it the other way around. But it will also overgenerate. So, for example, the example they've got here is that it would also make 3700. Now, if you're just using a finite state machine to do recognition, it doesn't matter that it overgenerates necessarily. If you just want to say, oh, yeah, this is in the language. But just to point out in this case that it does. This here, we've added an extra arc to go back to the beginning. The idea being that you could have an infinite list of dates. There is now a comma missing on here, I guess, on this arc, because you would need a comma to make the list. And that would change the vocabulary. We're also missing the start state again. I think the point in showing you this is that you could imagine now having something like anti-disestablishmentarianism without having to build an infinite finite state machine. You can have a finite state machine, finite number of states, and still get an infinite. Okay. So that's a quick reminder of your finite state machines. And again, if these were finite state transducers, what I could have on every arc is a symbol that it mapped to as it did the transition. So those would be, I'd need a vocabulary. I'd need to know what vocabulary I was allowed to use on my transitions as I mapped from one to the other. And I would also need to know which ones applied where. Okay, let's look again at this spelling rule. We're now going to build this as a finite state transducer. So this is the rule I showed you before, from box to boxes. So we want to create a finite state transducer that takes this string and maps it to this string. So you can think of finite state transducers as just creating a regular relation between strings, if you like. Okay, so we've got these two. Oops. Okay, so here's our finite state transducer. Every time we move on an arc, we take the input, some input, and we map it to some other input. And that's indicated on all of the arcs. Other here, I think, means anything other than the letter E. So, and I think our vocabulary, of course, is A through Z. And we'll assume that our starting state is 1. Okay? So here's the rule, and this is how we've built it. And you can see that the context on the right-hand side of the rule has actually just defined the structure of our finite state transducer. Okay, so using this, we should be able to do things like take the word cakes and boxes and turn it into its stem and affix, and actually should also be able to do that the other way round. Yes, if you think of reversing all of the pairings. Okay, so I think now we run through this just to show you how it works. So here we've got, we start with the B on boxes, and if you remember, all of the vocabulary was just circling around on 1, so we just go back to 1. Then, at any point, this is a non-deterministic finite state transducer with epsilon transitions. So that means at any point, we could, if we're in state 1, we could just move to state 2 if we wanted to, okay? And that's illustrated here as a possibility. It's a possibility at any point that we're in state 1. But we'll ignore that for the minute. We'll just circle through, so B, O, and now this arc here, the arc from 1 to 4, that had an X on it. Okay, so this tells us something. Let's go back to this previous diagram. So other here doesn't mean anything other than E. It means anything that isn't specified on any other branch coming out of 1. So this is everything except S, X, Z, and E has been marked explicitly here as well. Okay, so it's meaning the whole vocabulary set difference with the ones which are on these on arcs coming out of the same node. Okay, so we take the X. We're now in state 4. And this is what the input and output at this point has just stayed the same. Okay, each time we've transitioned, we've just done we've just output the same thing as we input. Now that we're in state 4, there were two options. On seeing the E, we could either go back to state 1, or we could go to state 2, having output this little affix stem. So we'll do both of those and keep track of that. Now, for the scenario where we returned to state 1 through having, which one is it? This one here. We could, as I said before, given we're in state 1, we can always just move to state 2. So that's a possible input at this point, which would put the affix here. And now, no matter which way we went, we've now ended up in states. Okay, sorry, there's two things. In two of our scenarios now, we ended up in state 2, and so now we can just output the S. And in one of our scenarios, we can just move. We went round using the E on the explicit E that was mentioned on arc 1, the loop on state 1. So that would allow us to come back to state 4. So, at the end of the day, what have we got? For the input boxes, we could have reached an accept state by having box affix s, by having boxes, or if we'd allowed ourselves to think of an epsilon transition between E and S, having boxy hat S. Right, so what good is this? This seems like nonsense, doesn't it? We've got, we took a word, we wanted to just take the S off, and we've ended up with 3 different possibilities. Well, what we would do now is go and look in a lexicon to see if any of these are valid stems. And we'd find that this one is the only valid stem, so we would ignore the others. And of course, these things are useful in the case where we have something like short and shorts, right? Because we want to keep these different variations around because we don't want to throw away the correct analysis. Okay, so just some more things about using finite state machines in this way. We assume tokenization at boundaries and that each word is split into characters. So each one of those arcs was dealing with a single character at a time. And as I said, once we get this list, we can look up the things before the affix marker to see whether they're valid stems. And if we look at it the other way around, we can do some generation. What you actually might think of ending up doing is you can think of it as there being 2 finite state machines, if you like, that are involved. So you could have, if you have something like boxes, you can imagine taking the boxes, getting to box affix S, like we just did then, and then having another finite state transducer that says, okay, this is a stem plus an ED. So you could think of having a composition of finite state machines that basically takes you from the word itself and deals with the spelling rules or the morphophonology, and another one that deals with the morphotaxics, if you like what is it that this affix, stem and affix might actually mean. So you could think of a whole mapping process and composing them together. What doesn't it do? It doesn't allow us to put the bracketing in any way on words like unionize and unionize. Because what we've got, if we look at the rules that we used in order to get that derivation, and we drew it out as a little tree, we'd just end up with a left branching or right branching tree. We wouldn't get anything that showed the structure of the word with the brackets. So we've shown you here the use of finite state machines for English morphology. And everything in natural language processing is about using the right tool for the job, okay? So English morphology, highly concatenative, quite regular. We can use these finite state transducers. They're really, really efficient to do so. If we had lots and lots more situations where we wanted to know the structure, like in unionized, with that, when we needed to know how to peel the things apart, we'd have to start using context-free grammars and something a bit more complicated. So it's about using the right tool for the job. You can do most things you want to do in English morphology by using this very, very simple and efficient idea. There are other things in natural language processing where you can use the same kind of efficient models. So dialogue processing is one, where you can imagine having a situation where you're in a given state and then you want to know how many people do you want for your booking in this restaurant? What time would you like to come? So that you can think of like managing the questions that you would ask in a dialogue by the information you know at the current state. So they're quite often used for modeling how a dialogue would be used. But I wanted to show you that this isn't sort of noddy stuff. This is actually a paper from 2015 or 16. Which uses composition of finite state transducers in order to figure out where to put the sentence boundaries in spoken language. So if you've got spoken language, then automatic speech recognition system, it just produces a transcript which has got no punctuation in it or anything like that, right? So there's no sentences, there's no sentence breaks. You have to figure out where to put those breaks in order to use other natural language processing technology on top. I can't parse a sentence from that speech, that spoken transcript, if I don't know where the sentence boundaries are. So this particular paper, it had 3 different finite state machines, finite state transducers, and they were based on different things. So one of them was based on the prosodic model. So this was taking information from the speech itself. And it was modeling things like when my tone falls, that would be indicative of the end of a sentence kind of thing. And it also looked at sentence length, and it also had a finite n-gram model of the possible things, of all the possible things that were said in the transcript. And what it did was it used them as transducers by saying at each point when I make a transition, I either insert a sentence boundary or I don't. Okay, so at every point you could possibly insert a sentence boundary if you wanted to. It then convolved all of these 3 different models, composed them together, and used a sort of Viterbi to see which is the most efficient path through all of these composed finite state machines to put that will make the most probable sentence boundaries for this particular text. So that's just to show that this thing, this is particularly neat because it pulls out the different things. It means if you've got some different sort of speech signal, so if I was looking at speakers of, native speakers of English, they might have one prosodic model. If I was looking at American speakers of English, they might have a different prosodic model, so I could just pull that out and use a different one. Okay, I think that's it for today. Oh, I have concluding comments. Okay, let's just see. English is an outlier in the world's languages, very limited inflectional morphology. Yes, so we called it a analytic language, limited inflectional morphology, derivational morphology, so it shares the properties of both. We've been able to use these kind of finite state transducers for a long time to solve most problems in English morphology. We don't even need probabilities. In the scenario where we had those 3 different possible outputs for boxes, we didn't need to, you could imagine putting probabilities on the different arcs in the finite state transducer. We don't even end up having to do that very often because there isn't that much ambiguity in terms of how to break it down, or because of the stems when we look them up in the lexicon. And there's actually loads of fun finite state kits that you can look at online if you're interested in playing around with this. OpenFST and various things. You can go build yourself something like the thing on the previous slide. It's all good stuff. Okay, see you on Wednesday.